Hello, my name is Drew Griffiths, and this is my presentation on Lab 1, Constant Velocity for Physics 2211. The purpose of this lab is to compare the position versus time graphs of an object moving at a constant velocity in the real world to its predicted position found from a computational model. So for this experiment, my system was a ping pong ball, the surroundings were the floor, and the observed position software that I used was Tracker. The fundamental physical principles for this lab are Newton's second law, Newton's first law, and the position update formula. Newton's second law states that the net external force is equal to the change in momentum divided by the change in time. As you can see on the right here, you can also calculate the velocity update formula from F net equals the change in momentum over the change in time. And Newton's first law states that an object at rest will stay at rest, and an object in motion will stay in motion unless it is acted on by an unbalanced force. And the position update formula is here in the bottom right corner. The procedure for this lab is to first record an object, in my case a ping pong ball, moving at a constant velocity without changing direction. The next step is to import the video into Tracker and capture the ball's position in each frame at a specific time interval. And next, I will edit the starter code in GlowScript to create a computational model for the ball's motion. And then I will enter the data into a spreadsheet to create a position versus time graph with both models in it. And then I'll compare the data to see the difference between my computational model and my actual experiment. So here is a screenshot of my Tracker software on the right. As you can see, here's the graph of the time versus position. And the initial position for my experiment of the ball was 2.335 meters on the positive x-axis, and the initial velocity was negative 3.45 meters per second, and the total time it took for the ball was 1.5 seconds. And here is the code in GlowScript that I used, and the only changes I made was I did not edit the mass, because in the velocity update formula, mass does not matter because F equals ma, and F net divided by m, the masses will cancel out, and the velocity is not impacted by mass. I set my initial position to 2.335 meters, and my initial velocity to negative 3.45 meters per second. I also changed the delta t to 1 over 30 because the frame rate was 30 frames per second on the video that I took. I set net force equal to 0 because that's the point, there's not supposed to be a net force acting on the ping pong ball. Otherwise, it would not have a constant velocity. And I also used the position update to predict position here. Did position equals position plus the velocity of the ball times delta t, which just updates the position using the position update formula that I showcased earlier. Here's my observed and predicted position graph. As you can see, the predicted position motion is a straight line, which means that there is a constant velocity. And the observed position graph in blue is different because it has outside forces impacting it, which the computation does not take into account. Both of them have fairly similar slopes, which means pretty similar velocities, but the observed position is not constant while the predicted position is. Some possible errors for my experiment are differing placements for the center of mass. As you can see on the bottom right corner, my tracking placements were not exactly horizontal, which they probably should have if I was putting it exactly in the center of mass, but it's very difficult to do that. So that created a little bit of error in the position for the ping pong ball. And then there's also varying friction and air resistance, maybe from the air conditioning in the room blowing the ping pong ball back. Then also the friction varies as you're going across the floor because of dirt and particles and other stuff on the floor, which would slow the ball's speed down and make it not have a constant velocity. Then the conclusion questions: what if the positive and negative x-axes were flipped? If these two axes were flipped, then the slope of my graph would be positive instead of negative. And also the velocity that I calculated would be positive. My velocity was negative because the ball started in the positive x-axis and then traveled to the negative x-axis. And also The net force is not zero due to friction slowing down the ball as it is rolling. If the net force was zero, the velocity would be constant the whole time as it is in the computational model, but friction and other forces, like I described in the last slide, they would slow the ball down and make it not have a constant velocity. Thank you for watching.